Hello, my name is Matthew Abate, and today I'm going to be speaking to you about some of the work that myself and my collaborator Corbin Klett have been conducting in the Georgia Tech Decision and Controls Lab and the Georgia Tech Facts Lab. The title of my presentation is Lyapunov Differential Equation Hierarchy and Polynomial Lyapunov Functions for Switched Linear Systems, and this work was advised by Dr. Sam Coogan and Dr. Eric Ferrone. Before I begin, I'd like to thank our funding agencies, including the Air Force Office of Scientific Research, and mention that an extended version of this work is available through Archive at the link provided. In this work, we consider switched linear system models as in 1, which is given by x dot is equal to ax, where a evolves non-deterministically for all time inside a finite set of switched modes. Such systems naturally arise in various areas within control theory, and the non-deterministic nature of the system facilitates the need for stability analysis tools. For instance, it is well known that the switched system 1 can be unstable, even in the instance that each switched mode is itself stable, and to illustrate this point, I've included an example on the next slide. Consider, for example, a switched linear system with two states and two modes, where we take the first mode to be the dynamics shown on the top left of your screen, and the second mode to be the dynamics shown on the bottom left of your screen. Both of these modal equations are themselves stable, and to illustrate this point, we've included the eigenvalues of the A matrix, as well as plots showing trajectories of each system. While both of the linear modes in this example are themselves stable, it is possible to construct a switching policy such that the switched linear system formed as the combination of these modes is unstable. This is shown on the right, where we consider the sample case, where mode 2 is taken anytime the system is in the first or third quadrant, and where mode 1 is taken anytime the system is in the second or fourth quadrant. As suggested by the previous discussion, the main focus of this work is to generate tools for assessing the stability of switched linear systems as an x dot is equal to ax. Stability type proofs for dynamical systems often involve the creation of a polynomial Lyapunov function which certifies the stability of the system. Specific to our case, we find some added structure, as it is known that a switched linear system x dot is equal to ax will be stable if and only if there exists a common homogeneous polynomial Lyapunov function which satisfies the Lyapunov constraints and certifies the stability of each switched mode individually. This is a well-known result, and for those who are not familiar with homogeneous polynomials, I've included an example at the bottom of this slide. A homogeneous polynomial is simply one for which the sum of the exponents on each monomial is equal. In this example, we provide a homogeneous polynomial of order 4 and note that the exponents on each monomial sum to 4. The simplest homogeneous polynomial Lyapunov function is the quadratic Lyapunov function, given as v of x is equal to x transpose px, where p is symmetric positive definite and satisfies the Lyapunov constraint 2. The benefit of searching for a quadratic Lyapunov function rather than a higher order homogeneous polynomial Lyapunov function is essentially computational. Quadratic Lyapunov functions are the simplest form of homogeneous polynomial Lyapunov functions and are thus the most easily identifiable. Moreover, the search for a quadratic Lyapunov function can be cast as in a semi-definite program, and many efficient solvers exist to handle such tasks. However, the switched linear system x dot is equal to ax can be stable even in the instance that a quadratic Lyapunov function does not exist certifying the stability of the system. This is unlike linear time invariant systems, where stability is possible if and only if there exists a quadratic Lyapunov function. As a second stability analysis tool, we next introduce the switched Lyapunov differential equation, which is given as 3, where the state of the system is now a matrix in n by n, and where A evolves in the same finite set of switched modes as was discussed previously. The switched Lyapunov differential equation 3 is stable if and only if the switched linear system x dot is equal to ax is stable. This is our result, and while we do not include a full proof here, I believe it is helpful to have some methodology and understand why the two equations are linked. In particular, we note that if x is a solution to x dot is equal to ax, then capital X, which is given as x transpose, solves the Lyapunov differential equation 3. Thus, stability of the system 3 is linked with stability of the system x dot is equal to ax. And in the following, we construct a hierarchy of linear switched systems from the Lyapunov differential equation 3, and it is shown that each of the systems in this hierarchy has the same stability properties. To that end, we next rewrite the switched Lyapunov differential equation in a linear switched form given as 4. The system 4 is switched linear with a state of dimension n squared, and the A matrices associated with each switched linear mode can be constructed using Kronecker products from the A matrices of the original switched linear system. Following from the methodology presented on the previous slide, we see that if x is a solution to x dot is equal to ax, then the Kronecker product of x with itself is a solution to the switched Lyapunov differential equation in its linear form given by 4. In the following, we refer to the system 4 as the metasystem relative to the system x dot is equal to ax. Applying the concepts of quadratic stability to the metasystem, we now have that if there exists a symmetric positive definite matrix P, which is an n squared by n squared, such that the Lyapunov constraint 5 is satisfied, then the system x dot is equal to ax is stable, and a fourth-order homogeneous polynomial Lyapunov function for that system can be formed using the equation 6. To reiterate, certifying the stability of the metasystem with a quadratic Lyapunov function identifies a higher-order homogeneous polynomial Lyapunov function for the initial system, and thus can be used to certify its stability. We refer to such Lyapunov functions as meta-Lyapunov functions for the system x dot is equal to ax because they are constructed from the higher-order metasystem. This creates an intuitive procedure for searching for homogeneous polynomial Lyapunov functions for switched linear systems x dot is equal to ax. That is, one can first search for a quadratic Lyapunov function for the system x dot is equal to ax by searching for a p-matrix which satisfies the Lyapunov constraint 7. If such a quadratic Lyapunov function does not exist, then one can search for a fourth-order homogeneous polynomial Lyapunov function by searching for a p-matrix which satisfies the Lyapunov constraint 8. In the following, we expand this procedure and create a method for searching for high-order homogeneous polynomial Lyapunov functions for the initial switch system, and this procedure only relies on the computation of a quadratic Lyapunov function for a related system in the meta hierarchy. Our main result is to provide a hierarchy of Lyapunov constraints 9, which are reminiscent of the initial Lyapunov constraints x transpose p plus pa must be negative semi-definite. In the case that a p-matrix is found which satisfies the Lyapunov constraint 9 at the cth level of the hierarchy, then a Lyapunov function can be constructed for the initial switch system which is homogeneous in the entries of x and is of order 2c. The form of this homogeneous Lyapunov function is given by 10. At this point, we pause to provide a discussion on the results presented thus far. Our main result is to provide an intuitive procedure for searching for homogeneous polynomial Lyapunov functions for switched linear systems, and this procedure does not require any heavy machinery to implement. There are, for instance, old techniques and tools for searching for quadratic Lyapunov functions, and our result shows how these tools can equally be applied to search for higher-order homogeneous polynomial Lyapunov functions as well. Despite the apparent structural advantages, there are few computational advantages to our approach at present, and this is due in part to internal redundancy built into the meta-Lyapunov constraints provided. To illustrate this assertion, I've included an example on the next slide. Consider a switched linear system x dot is equal to ax, where x evolves in R2. The corresponding metasystem is now given by 11, and the state of this system corresponds to the Kronecker product of x with itself. This is given as 12. Note that when beginning at an initial condition, x cron x, and evolving along trajectories of the metasystem 11, we find that the second and third entries of the metastate remain equal to one another. This is due to the construction of 11. We next consider a vector y, which contains the monomials of x of order 2, now with no redundancy. As we show in equation 14, this vector also evolves in a linear switched manner, where the switched linear modes can equally be constructed from the A matrix of the initial switched linear system. This new system 14 has reduced dimensionality as it only considers a vector of 3 entries rather than a vector of 4 entries as presented on the previous slide. And in the following, we build in this dimensionality reduction into our search for meta-Lyapunov functions in order to create a computationally competitive procedure for searching for high-order homogeneous polynomial Lyapunov functions for switched linear systems x dot equal to ax. As such, our second result is to show that a vector containing the c-th order monomials in X will also behave in a linear switched manner. Thus, the search for high-order homogeneous polynomial Lyapunov functions for the initial switched system x dot is equal to ax can be cast as the search for quadratic Lyapunov functions satisfying the meta-Lyapunov constraint 16. In our work, we also provide an analysis and discussion contrasting some of squares-based techniques for searching for homogeneous polynomial Lyapunov functions with the new meta-Lyapunov technique presented here. While due to space constraints we are unable to provide this discussion here, we refer the interested reader to our publication. To conclude our work, we next present a numerical example detailing the methods of this paper. In particular, we consider a system with 2 states and 2 switched modes, and in this example, we compute meta-Lyapunov functions for this system of orders 2 through 26. To visualize these homogeneous polynomial Lyapunov functions and their benefits in comparison to one another, we show a plot with an initial state of the system in the reachable set which is able to attain through trajectories of the switched linear system x dot is equal to ax. This reachable set is shown in yellow. The system is stable, and it is well known that the reachable set of the system, which emanates from the initial state, will always be contained inside the sublevel sets of the Lyapunov function which certifies the system's stability. Here we plot level sets of orders 2, 10, 16, and 26 which cross the initial state, and we see that high-order homogeneous polynomial Lyapunov functions tend to hug the reachable set in a tighter fashion. This is reminiscent of the fact that quadratic Lyapunov functions can only be used to provide elliptical reachable set approximations, whereas high-order homogeneous polynomial Lyapunov function approximations can be constructed with more interesting geometries. Thus, even when a quadratic polynomial Lyapunov function is known which certifies the system stability, it is helpful for a system designer to compute higher-order homogeneous polynomial Lyapunov functions in order to attain better estimates of reachable sets in infinite time system behavior. In our work, this example is presented in conjunction with an algorithm for generating high-order homogeneous polynomial Lyapunov functions using the meta-Lyapunov technique presented here. We also provide a comparison between our approach and a similar approach directed by some of squares-based techniques. While we are unable to provide a full analysis here as to the differences of our approach, we refer the interested reader to our publication. In conclusion, in this work we show an equivalence between homogeneous polynomial Lyapunov functions for switched linear systems and quadratic Lyapunov functions for a related hierarchy of Lyapunov differential equations. A computationally competitive algorithm is presented for generating high-order homogeneous polynomial Lyapunov functions in this manner, and in our work we also contrast a similar search using SOS-based techniques. Thank you for listening.